Wonderful morning, everybody. Respected speaker of the day, Dr. Chandrasekhara, program convener, Dr. Sendil Kumar, and the learned delegates, we welcome you all for today's webinar on behalf of the management and our team. Today's FTP session will be focusing on spectral quasi-linearization approaches for solving boundary value problems in fluid mechanics. Now, I would like to introduce our resource person of the day, Dr. G. Chandrasekhara, Assistant Professor of Mathematics, BMS College of Engineering, Bangalore, has around 10 years of experience in teaching. He has completed his PhD in Bangalore University, his MSc and BSc Mathematics also in Bangalore University. He has received Best Mathematical Model Award in a third graduate modeling camp from Oxford University, Oxford, UK. He has also visited abroad countries on academic basis to Oxford University and Cardiff University, UK, and Korean Institute of Science and Technology, Republic of Korea. He serves as a member in 3 academic national bodies of ISTAM, IMS, and IAENG. His area of research specializations are heat and mass transfer, homotopy analysis method for fluid flows, convective instabilities and surface instabilities. Lattice-Boltzmann modeling of fluid flows, spectral methods for fluid flow problems. He has published around 15 research publications and also presented and participated in many international and national seminar, conference, workshop, etc. He has also been invited as a resource person in many colleges. We are very much honored and proud to have you as a resource person, sir. Thank you so much for accepting our invitation. Now, I request Dr. Chandrasekhara, sir, to proceed with this presentation.
Okay. Thank you for your kind introduction, madam. I welcome all the participants of this today's national webinar on fluid mechanics organized by KJISL Institute of Technology, Coimbatore, Tamil Nadu. First of all, I would like to thank the management, principal, vice principal, and the entire organizing team for giving me an opportunity to share my knowledge in this today's national webinar on fluid mechanics. So I hope all the participants got some insights from yesterday's session, which was wonderful, given by Professor Abdul Hakim. So he has given complete insight into the applications of fluid mechanics, in particular the application of nanofluids in industrial application and medical applications, and also he has given the complete details on how to model the boundary layer flows with respect to nanofluids. So in continuation of that talk, so today I'm going to present on the post-processing of that mathematical modeling, whatever yesterday Akim sir has explained. So today's my topic of the talk is spectral quasilinearization approaches for solving boundary value problems in fluid mechanics. So as we know, fluid mechanics is uh, it is a actually engineering subject, but many of the physicists, the people from chemical engineering, biotechnology, and mechanical engineering, civil engineering, and also from the mathematics, they are very much fond of this fluid mechanics. So most of the mathematicians, they are studying this fluid mechanics as a theoretical subject. So whenever we are studying some subject theoretically, we are planning to, or we are try to model that the phenomena of that subject or concept by means of mathematical equations. So thus mathematical equations are called mathematical models. So most of the mathematicians are interested in modeling fluid mechanics problems as a mathematical equations. So when I say mathematical equations, these equations may be linear, just a algebraic equations, but we won't get any just simple algebraic equations in fluid mechanics. So instead of simple algebraic equations, we'll get a the equations are called differential equations. I hope most of the participants know what is a differential equation. So this fluid mechanics problems can be modeled as a differential equations and also integral equations. So whenever we have a differential equation or integral equations, so we need to understand the fluid flows or the fluid properties in fluid mechanics. So one has to solve this system of equation, differential equations or integral equation. Uh, to solve this system of differential or integral equations, we have to use one or the other method uh, to find the like the flow properties or flow fields like velocity, temperature, concentration, and so on. So since the fluid mechanics, fluid flows or the behaviors of fluids are highly nonlinear, so most of the times we'll get a nonlinear differential equations. So in this talk, I'm going to explain how to solve the nonlinear differential equations that modeled from the fluid mechanics. So first, I would like to give some brief motivations to the researchers who are just started the research in fluid mechanics. So first, I'll just explain why we required numerical methods. Then I'll go into the this spectral quasilinearization method for solving the differential equations. So for the outline of today's my presentation is, first I'll just give a brief motivation on numerical methods, why we require numerical methods. Then I'll just give some list of different numerical methods that are available for solving differential equations. Then I'll jump into the spectral quasilinearization method. In that, first step is the approximation of a solution of a differential equation. In the second step, I'll explain how to discretize or collocate the points in the physical domain. Then the central part or central part of this entire talk is the differentiation. So I'll explain how to represent the derivatives of some functions in terms of matrices. This is the art of this entire talk. So then I'll explain one example on linear ODE, and I'll take some case study problems from fluid mechanics as nonlinear differential equations. Then I'll explain how to convert this nonlinear differential equation into linear form by using the method called Quasilinearization. Then we'll discuss the results of those problems. And very important point is, I'm not going into the partial differential equations in this talk because the time is the main constraint here. So therefore, I myself restrict to the ordinary differential equations. So let me start with the first part to motivate the researchers who are just started their research. So first of all, we must know why we required numerical methods. So why we require numerical methods is because of the following reasons. So we know that most of the real world phenomena are nonlinear in nature. So whenever we use a mathematical modeling, so we can model them as an integral equation or differential equations. So most of the models we can model it as a differential equations. So whenever we model them, the phenomena, real world phenomena like physical phenomena or chemical phenomena or biological or any phenomena has a differential equation, we can categorize that differential equations as a linear and nonlinear differential equation. So we already know that there are methods to solve linear differential equations. We have both the numerical method as well as analytic method. So we can obtain the closed form solution of many of the linear differential equations. But for nonlinear differential equation, there is no closed form solution or analytic solution for nonlinear differential equation. So this is why we required numerical methods to tackle with this nonlinear differential equation. Then why we require numerical methods is because of the another reason I've given here. So numerical methods of capable of handling large system of equations and also different degrees of nonlinearities. So we already know that by manual calculation we can go up to 4 equations, 4 unknowns. But if you have n equations, n unknowns, then it is very difficult to solve by by manual calculations or hand calculations. Therefore, one has to go for a numerical methods. So the other reason why we require numerical methods is whenever we have the complicated geometries or irregular geometries and the differential equation associated with those irregular geometries, it is impossible to solve those differential equations analytically. So in this case, this numerical methods plays a very important role. So to take care about the irregular geometries or complicated geometries. So this is also main reason for why we required or why one has to learn the numerical methods. The other thing is we know that whenever we are studying some phenomena or we are developing some system, it is the resources are main constraint there. Uh, so if we try to develop the system as it is, then it is a very it cost lot of resources are required. Also, it is a cost effective. So instead of developing actual models, if we develop the prototype or if we simulate by using computer technology, then it will be less cost effective. Therefore, so these numerical methods are used for simulation. And if we do the simulation before developing actual models, it will be less cost effective. And the other very important point why we required or why one has to learn numerical methods is there is a rapid development in mathematical softwares and tools. Also, there exists a parallel computing now, and also the speed of the computers are increased, storage capacity of the computers are increased. So because of this, one has to know the numerical method and numerical programming by using some mathematical software or tool. So there are plenty of softwares are available. To mention few, so there exists a MATLAB is a very useful software, and it is a nowadays it is both symbolic as well as a numerical software. And there is a complete symbolic software called Mathematica, and there is a completely simulation software called Console, and there's a open source software called Python. There are many software tools are developed because of this advancement in numerical methods. So because of this reason, one has to, those who are yet to start or just started their research in fluid mechanics must know one of the other numerical methods and also the programming mathematical softwares or tools. So then I'll just try to list out the different differential equations. This is just to motivate the researchers who have just started their research. So these differential equations may come either by modeling some phenomena, or they will come while solving the partial differential equations by using series solution method. So while solving the Laplace equation in polar or cylindrical coordinates, cylindrical or spherical coordinates, will get what is called as Bessel differential equation. So this is a Bessel differential equation. You can observe that this is a linear differential equation with variable coefficients. So x square y double dash plus x y dash plus x square minus n square into y equal to 0 is called a Bessel differential equation of order n. So this is the linear variable coefficient differential equation. This we can solve by using series solution technique. And the whatever series solution we get out of this Bessel differential equation are called Bessel's polynomials or Bessel functions. They plays a very important role in this spectral collocation method. Similarly, if we solve that steady state distribution or Laplace equation in spherical or cylindrical coordinates, will get another variable coefficient differential equation called Legendre's differential equation. So it is of this form. Similarly, we get the few more differential equations like Legendre differential equation, Chebyshev differential equation, and the Hermite differential equation. So the solutions or the polynomials or functions associated with these differential equations plays a very important role in spectral collocation method. Then we have a equation called Faulkner's-Kahn equation from fluid mechanics. It is one of the famous equation in boundary layer theory. So this is it's a nonlinear differential equation. I'm going to explain how to solve one of the kind of this Faulkner's-Kahn equation. It is a modified one. It is called Jeffrey-Amell equation. So I'm going to explain at the end of this at the some stage I like going to explain the how to solve this nonlinear equation called Jeffrey-Amell equation. Then we have a set of differential equations. They are derived from partial differential equation. They are modeled from the actual phenomena, physical phenomena called heat equation. Then wave equation. We have a Laplace equation and a Poisson equation. So this heat equation, wave equation are they are unsteady equations, whereas Laplace equation and Poisson equations are steady equations. They represents the heat diffusion. The first equation represents heat diffusion, and Laplace equation represents the heat diffusion in steady state. Similarly, we have the nonlinear equations from quantum mechanics called Schrodinger equation, and the nonlinear equation from fluid mechanics is called Navier-Stokes equation. So this is the central part of this entire talk. So Navier-Stokes equation. It is a highly nonlinear differential equation. More than that, it is a vector differential equation. So it has this system of equations here, not only one equation. So and also it is a partial differential equation. So this is the central part of fluid mechanics. So based on the different fluids, different geometries, there are many researchers in the world. They are modeling this equation with respect to some limitations. So I'm going to explain how to solve this in some limited cases. There is a mathematical model associated with economics also. So it is called Bloch-Scholes equation. This equation comes from the European option pricing. That, and also there are partial differential equation associated with electromagnetics also. So they are given by the Maxwell's equation. So these are the set of Maxwell's equations. So this list is not limited. There are many other differential equations also. Just to motivate the researchers who are just started their research, have given this list. Then there are several numerical methods available for solving the differential equations. To mention a few, these are the list of different different methods available to solve the initial value problems called Euler's method, Taylor's method, Picard's method, Runge-Kutta second order and fourth order methods. So nowadays, the many researchers are using Runge-Kutta hybrid of nature of Runge-Kutta hybrid methods to solve the boundary value problems. So there is a list of methods available to solve partial differential equations and boundary value problems. So to name few, the shooting method is used to solve boundary value problems, and finite difference method. There exists a finite element method, a finite volume method, and there exists a spectral method. So today in this talk, I'm going to elaborate on this spectral methods. In particular, in spectral methods, there are class of methods called the Galerkin method, but I'm not going into this Galerkin method. but I'll explain in detail the spectral collocation method or pseudo spectral method in this talk. There exists a Chebyshev method, Chebyshev tau method also. Then to tackle with the nonlinear differential equations, there are several methods, but I'm going to explain how to use the Quasilinearization method to reduce the nonlinear differential equations into linear differential equations. So this is just to motivate the researchers who have just started their research. I've given the list of the methods and differential equations. Now let us start with the today's topic. It is a spectral uh, Quasilinearization method or pseudo spectral method. So the pseudo spectral method can be applied to linear differential equations by following the steps I mentioned here. So the steps involved in pseudo spectral method for solving linear differential equation is as follows. In the first step, you approximate the solution of some linear differential equation as a linear combination of basis functions. So then in the next step, we discretize the physical domain by using the collocation points, and then further you define the expression for residuals about these collocation points. Then next you form this set of all n plus 1 equations. Then you try write this set of equations in matrix form. Then solve this matrix system and express solution graphically. And then we can do so all the post processing uh, formalities of this solution. Then why we required pseudo spectral methods is because of the following advantages. These pseudo spectral methods, in pseudo spectral methods, we can compute the derivatives exactly. So this is the main ingredient or main part of this pseudo spectral method. So we can compute this derivatives exactly. So how to compute this derivative exactly, or that I'm going to explain in detail in the coming slides. But this derivative is called Chebyshev differentiation matrix. So this maps the functional values to the derivative values at the grid points. So that is y dash j is mapped to d times y dash j. So this D plays a very important role. So in this spectral collocation method. Then the second important point or advantage of this pseudo spectral method is it is having an exponential rate of convergence. So in space. So in terms of order of accuracy, this method is having an infinite rate of convergence. So you will see that with the example I'll explain. So the convergence of this method. And the other advantage of this spectral method is we can fix the basis functions that are well suited for particular problems. So each problem we can keep on changing this basis functions based on the requirement of the for the particular problem. And this method is actually it is the method which is derived from finite difference. Also, it is a finite element method. So it is you can call it as a hybrid method. So therefore, this is often more accurate than finite difference method with same number of degrees of freedom. So then pseudo spectral method uses so it uses global basis functions, but whereas finite element method uses local basis functions. So this is therefore this method is very similar to finite difference method as well as finite element method. Then uh, in the next slide, I'm going to explain the steps I mentioned for a particular example by considering general second order linear differential equation. So the but the main point in a spectral method is we'll try to find or approximate the solution u of x, capital U of x, to a differential equation of the form L of ux is equal to f of x, where L is the linear operator subject to the boundary condition So the left boundary condition BA and right boundary condition BB. So here the operators L, B, and BA, BB are linear operators. So we'll consider the second order linear differential equation in the general form. So like this as given in equation 1, subject to the conditions like this. So U of A is alpha, U of B is beta. We'll solve this differential equation by this collocation method. To solve this, I'll just use the steps I just mentioned in the previous slide. So the first step is approximate the solution. So how to approximate the solution is given here. So approximate this solution of this differential equation as a finite sum of some basis functions. So you take u of x is summation I is equal to 0 to n ci times pi I of x. So it is a linear combination of some basis functions from the functional space. So this basis functions maybe you can consider monomials like just 1x, x square, x cube, and so on. So this will take in series solution method. You can take this basis function as Bernoulli's polynomials like b naught x, b1x, and so on. You can also choose this basis functions as Chebyshev polynomials as t naught x, t1x, and so on. You can also choose this basis functions as Legendre polynomials. But so I'm going to explain by choosing what is called as Lagrange's polynomial. So this basis function pi I of x, you can choose any of this, but this list is not limited. You can use the other the functions like trigonometry functions or first Fourier transform coefficients or Fourier transform coefficients and wavelet transform coefficients and so on. So but I'm going to explain by taking Lagrange's polynomials into account. Then the next second step in this collocation method, as I mentioned, is the discretization of the physical domain. So the physical domain can be discretized either by using uniform grid or non-uniform grids. So the uniform grid is actually used in the finite difference method, but in this case we use the non-uniform grid instead of uniform grid. So why non-uniform grid plays a very important role, or how it increases the accuracy of the solution, we'll see that with the examples. But the main principle in collocation method is that the differential equation must be must satisfied at this at certain points within the interval AB, and these points are called collocation points. So how to discretize this interval AB? AB is given here, so we can use the collocation points like this. So xj is a plus b minus a by n into j in the interval AB. So these points are just every time b minus a by n into j is an increment. So we'll get the equi-spaced points, or we can discretize by using unequally spaced points as given xj is a plus b by 2 plus b minus a by 2 times zj. But this z is the very important point, and that z is given like this. It is a cos of pi j by n. So this z is equal to cos of pi j by n is called Chebyshev Gauss-Leberto points, or in short you can call them as a Gauss-Leberto points. So this is the we use this to discretize any physical domain while solving this any differential equation by a collocation method. So this, if we discretize that, we'll get the structure of the grid, unequally spaced grid like this. So you can see that the Gauss-Leberto points are given in red. So the number of points which is deposited near this end point, so -1 and +1. So number of points which are deposited at the ends of the interval is it is large number of nodes are they deposited near the ends of the interval. So this plays a very important role in boundary layer flows, because the effect of viscosity or the temperature and so on is significant near the walls. So to take care about that the significance of viscosity or temperature and so on, so one has to So capture all the information near the walls. To capture this information, this Gauss-Leberto points plays a very important role. So here, blue color dots are called equally spaced points, and red color points are called the collocation points. The other important point about this collocation points is you can observe that this is a about zero. This is symmetric. So about the line x is equal to zero, this the points on left side and right side are symmetric. So therefore, whenever the fluid mechanics problem with symmetry, this points plays a very important role. And if you apply this method for the problems having symmetry, this method will give the more accurate solutions. And so why we required this type of the discretization is because of following phenomena. First phenomena is called the Gibbs phenomena. So whenever we are doing this interpolation using this uh, spectral functions like cosines and sines and so on, or Fourier coefficients, this will perform very poorly for non-smooth functions. So whenever we have some discontinuous functions, this spectral interpolants with cosines and sines will perform very poorly. So therefore, so if we just go ahead and treat the problem on bounded domain as a periodic problem, so using this periodic extensions of cosines and sines, then there will be a jump, the resulting jump that may arise at the end point. So at the end points, there will be some troublesome if we consider the bounded interval. So therefore, this type of phenomena, the whatever we are missing at the boundaries is given by what is called as Gibbs phenomena. And due to this Gibbs phenomena, there will be a significant degradation of the accuracy of the uh, solution. So to overcome this, we are not using trigonometric polynomials as basis functions. Instead of that, we use algebraic polynomials as a basis functions. So this is what is called as Gibbs phenomena. Then why we need to discretize using the Gauss-Leberto points or similar to Gauss-Leberto points is because of this. Another phenomena is termed after Russian mathematician. Uh, uh, it is a Runge phenomena. So what is this Runge phenomena? Means the effect of interpolating with algebraic polynomials that distributes the interpolation nodes in the bounded interval will have high accuracy, and this effect is called Runge phenomena. So uh, so if we interpolate with the algebra polynomials, then the number of nodes placed near the walls is more in the bounded intervals. So this the number of nodes which are clustered near the uh, walls of the bounded interval will lead to the accuracy of the solution. So will increase the accuracy of the solution. So because of this phenomena, so we always try to use the clustered grids instead of equispaced grids. So these clustered grids are called collocation points. So in fact, this whatever I mentioned, Chebyshev or Gauss-Leberto points, uh, they yield a set of such clustered nodes on the standard interval -1 to 1. So the as I shown in that figure, so number of points placed or deposited near the walls is more. So therefore, we can capture the actual phenomena of physics near the walls. And further, this interval or this cluster nodes can be easily mapped to actual interval AB by using just a linear transformation. This I'll show how to map that in the next slide. But what is this Chebyshev points are the Gauss-Leberto points are nothing but they are extremal points of Chebyshev polynomials. So Chebyshev polynomials comes from the they are solutions of Chebyshev differential equations. So only I mentioned those differential equations at the beginning. So then, as you observe that figure I've shown, the Chebyshev points are equally spaced on the unit circle. So therefore, we can observe there is a nice connection between spectral differentiation in on the bounded intervals with the Chebyshev nodes. So therefore, so the derivatives are converted into differentiation matrices that will be derived shortly. So in this lecture, I'm not using the trigonometric functions or post Fourier transforms. Instead of that, I'm using only the Chebyshev differentiation matrices. So, but one can use this post Fourier transform in case of in place of Chebyshev differentiation matrices. But that is not the interest in this talk. So then these are the examples for the different type of collocation points. So this is already mentioned. So cos pi j by n is called Gauss-Lebedev points. So j is 0. This is minus cos of 0. This plus 1, and j is equal to n. This is cos pi is minus 1. So therefore this interval is a bounded interval minus 1 to minus 1 comma plus 1. There exist other type of the collocation points are called Gauss-Chebyshev points. Then there exist Gauss-Rodin points. So these are the different type of points, the collocation points that exist. You can use any one of them while solving the examples. But I'm using Gauss-Lebedev points to explain, to demonstrate the method applied for nonlinear and linear differential equations. Then, so how to convert the Gauss-Lebedev points or collocation points from the physical domain to computational domain or Chebyshev domain, and vice versa. So we can use this linear transformation. Xi is a plus b by 2 plus b minus a by 2 into zi, where zi is the collocation point given by Gauss-Lebedev. So this transformation, these two transformations we can use from the physical domain to computational domain or Chebyshev domain, and Chebyshev domain to physical domains. So while solving problems, you can use this switching. So then the next step in this collocation method is we'll try to evaluate this entire differential equation about this collocation points. Suppose if x0, x1, so on up to xn are collocation points, then approximate this solution capital U of x. The example we considered at each of these points. That means I'll just substitute x is equal to xi. So then this is the differential equation about this collocation points x0, x1, x2, so on up to xn. So then differential equation becomes like this. So, and these are the boundary conditions. This is a left boundary condition at x0, and this is the right boundary condition at xn. Then the next step in this collocation method is defining a residual. So the residual of the differential equation, the linear differential equation we considered, is defined as follows. We just take this right hand side r of x to left hand side and substitute the approximated solution capital U in place of small u. Then the difference between whatever values we get after replacing small u by capital U are called residuals. So this is you just compute residual at each collocation points. So this is the residual. So if this residual is very small or very close to zero, then capital U will be the best approximation for this differential equation. So therefore, this collocation method or quasi-linear spectral collocation method is nothing but minimizing this residual. So therefore, we can view this collocation method as to minimize the residual or by making it vanishes at the interior collocation points. So because boundary conditions anyway it will satisfy, so we want this residual to be minimum at the interior points. And so this residual we can calculate by substituting that the series solution I mentioned. I just substitute series solution in the residual definition. So we'll get this equation. Then if I expand this equation at each collocation points and expand this summation, then we'll get n minus 1 equations, but this CIs are n plus 1. So there are n plus 1 unknowns. So and we have two boundary conditions. From the two boundary conditions, we'll get two more equations like this. So this is the left boundary condition. This is because of right boundary conditions. Then we can form the system of n plus 1 equations in n plus 1 unknowns given like E naught, EJ. So EJ are the equations at the interior points. E naught is the left boundary condition, and En is the right boundary condition. So this system will give n plus one equations in n plus one unknowns. So therefore, that system is given as E naught, E1, E2, so on up to En equal to 0. So this is n plus one equations in n plus one unknowns, C naught, C1, C2, so on up to Cn minus 1, Cn. And so this, therefore, the collocation method can also be viewed as generating the system of equations. So once we solve this system of equations by using some method, then we'll get this constant C naught, C1, C2, so on up to Cn. Substitute back this in the assumed solution, summation Ci into pi of x, we'll get the required solution y. So that is the overall method, but this we can represent the system of equations in this matrix form. So so then we can solve this the matrix system. So here this matrix is, it is just a, there you can see that it is pi I double dash plus p times pi dash q times pi is the, it is, it is a differentiation matrix. So how to get this differentiation matrix is the very important point in this spectral collocation method. So just solving this system of equations for C naught, C1 up to Cn, so we'll get the required solution. So this solution to be approximated by solving this system of equations and substitute back this constant values in the capital U of x. This is the overall method to how to use this spectral collocation method to solve any differential equation. But this method, one must remember, this method is applicable only for linear differential equation. If there is a nonlinear differential equation, then one has to reduce into linear form by using the any alternate method. So one of the alternate method is a quasi-linearization method that I'll explain shortly. So now, before jumping into the problem, solving a differential equation, let me just quickly give some important properties of Chebyshev and Lagrange's polynomials. So this is the Chebyshev polynomials are t naught is 1, t1 is x, t2 is 2x square minus 1, and this is the recurrence relation for general Chebyshev polynomials. Tn plus 1 is 2x times tn minus tn minus 1. Then these are the L of x is product of this x minus xm divided by xj minus xm, are called Lagrange's polynomials. So this Chebyshev and Lagrange's polynomials will satisfy the Kronecker delta property. Uh, so this is pi j of xi is 0 for j not equal to 1, and 1 for j is equal to, j is not equal to I, it is 0, j is equal to I, it is 1. So if we choose the polynomials having this property, then it is very easy to formulate the collocation method. So therefore, so in this, while solving examples, I'm using the Lagrange's polynomials instead of other polynomials I mentioned. So we'll restrict ourselves to legendary polynomials and Gauss-Lebedev points. So then the final step in this spectral collocation method is how to generate this differentiation matrices. So this is the heart of this collocation method. So therefore, in the our last step in preparation for the solution of general boundary value problem is to determine the entries of this differentiation matrix. So how to define this entries of this differentiation matrix is given here. So once we discretize this interval minus 1 to 1 by using collocation points, Chebyshev collocation points, then we can determine the values of the function at each of these collocation points. The values of the function at each of this collocation point is given by this vector y. Then you at using this collocation points and this function values at the collocation points, one can interpolate or use the interpolation technique by using Lagrange's interpolation. So you can find the Lagrange's polynomial L of x of degree at most n. So that interpolates this values, the collocation points in minus 1 to 1, and the functional values in that collocation on the collocation points by using this relation. So L of x is equal to y. So this is the polynomial of degree at most n. So and it is called Lagrange's polynomial. So then to obtain this spectral differentiation matrix, you just differentiate this Lagrange's polynomial, whatever we get after interpolating it. So differentiating that, we can say that this y dash is equal to L dash. So using this relation, one can define what is called as differentiation matrix. So we can say that y dash is equal to dn of y. So this is the mapping I mentioned in the beginning. So this spectral collocation method is nothing but a mapping the functional values to derivative values. So that mapping is called the spectral differentiation. So differentiation matrix, this capital D. So now, so before taking examples, let me give how to calculate this differentiation matrix D for taking some examples. So first example, let us consider n is equal to 1. So if n is equal to 1, then the interval minus 1 to 1 will have only one subinterval. So therefore, they will be having the endpoints as points. So x naught is 1, x1 is minus 1. So then if we interpolate this by using Lagrange's polynomial, we'll get so the Lagrange polynomial like this. Here x1 is minus 1, x naught is 1. Substituting here, we'll get the Lagrange polynomial like this: x plus 1 by 2 into y naught plus x minus 1 by 2 minus 2 into y1. So then, so to find the differentiation matrix, we just differentiate this Lagrange's polynomial. So we'll get so y dash dy by dx is nothing but L dash, that is dl by dx of this. So we'll get this derivative is off into y naught minus off into y1. So now you this y dash you evaluate at this collocation points x naught and x1. So then we can write that in the form of matrix. So dy by dx is, there's a system of equations. Y naught and y1 are unknown. So this we can represent it as a matrix given here. So 2 by 2 matrix with the entries minus 0.5, minus 0.5, 0.5, and minus 0.5 into y naught y1. So this is a vector and this is a differentiation matrix. So therefore so y dash is mapped to y by means of this differentiation matrix. So therefore we can write dy by dx is just a capital D into y. So here I've written d2 because it is a 2 by 2 matrix. So if we take one collocation point, then we'll get a 2 by 2 matrix, 2 by 2 spectral collocation matrix, or Chebyshev. It is also called as a Chebyshev matrix. And I'll take one more example. So for n is equal to 2, then the interval minus 1 to 1, we can divide it into 3 points. So because it will be having two subintervals, so the points will be, so x naught 1, x1 is 0 midpoint, and x2 is minus 1. Then if we interpolate this by using Lagrange's interpolation polynomial, so we'll get y is equal to L of x. So this is the Lagrange's interpolation polynomial. So now you differentiate, if we differentiate this Lagrange's interpolation polynomial, we'll get the y dash is like this. So y dash is like this. Now, so y dash is nothing but L dash, and evaluate this at each of these collocation points. So x naught is 1. So if I evaluate at x naught, then I'll get one equation. And if I evaluate at x naught, x1 is 0, then I'll get second equation. And x2 is equal to minus 1, I'll get third equation. So that we can represent it as a matrix. So like this. So there are the three equations in terms of y naught, y1, y2. So this, if I write in the matrix form system of equations, I can represent that as a matrix 3 by 3 matrix given here into the vector y naught, y1, y2. So therefore the dy by dx is mapped to y naught, y1, y2 by means of this differentiation matrix. So hence, thus y dash in terms of two collocation points is given by d3 times y. So yeah, number of collocation points are 2. So 2 subintervals. Therefore, we got 3 by 3 matrix or 3 by 3 Chebyshev matrix or spectral differentiation matrix. So therefore, this we can use directly while solving examples. Wherever the first derivative is there, you can replace it by capital D. Second derivative, you can replace it by capital D square, and so on. So that means this mapping, the basis function of this works only for Lagrange's polynomials. basis functions or Lagrange's polynomials, then you can replace the derivative of Lagrange polynomial by it's capital D. So if it is a first derivative of Lagrange polynomial, you can write just capital D. Second derivative means you can write D square and so on. So these are the derivatives of Lagrange's polynomials. So the first derivative here, and the second derivative here, and third derivative here. So therefore, this matrix you can evaluate like this. This matrix you can evaluate like this. So the entries are already shown for n is equal to 1 and n is equal to 2. So these are the entries. So n is equal to 1, this is 0.5. We'll be having only this part, 2 by 2 matrix. It's 0.5 minus 0.5, 0.5 and minus 0.5. So this is for general n. So we'll be getting this matrix is n plus 1 by n plus 1 matrix. So this matrix is the called Chebyshev differentiation matrix. So therefore this y dash we can write it as just d times y. And similarly y double dash we can write it as d square times y, and y triple dash is d cube times y, and so on. So here d is called the differentiation matrix, and it is of order n plus 1 by n plus 1. So we use this matrix while solving examples directly. So now the how to write this D matrix or Chebyshev differential matrix entries in general. So these are the entries of this Chebyshev matrix. So off diagonal elements are given like this, and diagonal elements are given by this expression, and the first element on diagonals and last element on diagonal is given by this expression. So this here Cj is given like this. So now you can use this is this differential matrix is best explained in the spectral methods by Lloyd Trefton. So he has given MATLAB code for that generation of this Chebyshev matrix. So this is the just for beginners I've given code here. This is available in Lloyd Trefton book called Spectral Methods Using MATLAB. So one, you can generate this differentiation matrix by using this MATLAB code. So once you generate this the Chebyshev differentiation matrix, then wherever you have a derivatives, that derivatives you can just replace by this matrix. So if you replace that matrix, then it becomes just a complete matrix system. So if you solve that matrix system, you will get the required solution. So to demonstrate this matrix, this method, I've considered the one linear ODE. Then I'll jump into the examples from fluid mechanics. So let us consider this variable coefficient linear differential equation like this. So it is 1 plus x square into y double dash plus 4x y dash plus 2y equal to 0. The interval I've taken interval is minus 1 to 1 itself. Therefore, there is no need of changing the physical to computational or computational to physical. It's already in Chebyshev domain. So therefore, so we can directly assume this solution of this differential equation by using Lagrange's polynomials as basis functions. You observe that yj's becomes just constant. So it is a the y value at x0, y value at x1, and so on becomes just constants. So you assume the solution of this differential equation by using Lagrange's polynomials as basis functions as given in this equation. Then the next step is you collocate the entire domain. So you discretize the domain minus 1 to 1 by using this collocation points x0, x1, x2, so on up to xn. Then you evaluate this differential equation about those collocation points. I'll just replace by x by this xi. So then we'll get this is the differential equation about each collocation points. Then you substitute that solution. So whatever solution we assumed in terms of Lagrange's polynomial here. So if I substitute that, this becomes summation yj into lj double dash, and this becomes 4xi into yj times l dash, and so on. So this is the solution, substituting the assumed series solution in the differential equation. Then you expand this summation for also you compute at each collocation point. Then we'll get what is called as a system of equations. Those system of equations we can represent it as a matrix form, as I mentioned. So this matrix is nothing but aij is nothing but a differential operator. So this is the differential operator. So into this y vector is equal to right hand side. Since it is a homogeneous equation, this is the right hand side. Then after applying the boundary conditions, right hand side, the this is the right boundary condition, and the bottom last row you can implement the left boundary condition. Then this is the complete system of linear equations of this form. Ay is equal to r. So hence, if I solve this by any method, so we know that solution of this system of equations is just a inverse times r. So we'll get the required solution y. But this y is just a y of x0, y of x1, and so on. So it is a values of y at the collocation points. So that will give a required solution. But since just going back, since we are using a Lagrange's polynomial, so this entire equation 11 in matrix form is not required. So you can use just the Chebyshev matrix or differentiation matrix, spectral differentiation matrix. So therefore, this L double dash we can replace it by d square. L dash we can replace it by d. So where d is the differentiation matrix of order n plus 1 by n plus 1. So therefore here there is no derivative. So hence we'll get in this last term the identity matrix of order n plus 1 by n plus 1. So using that, so differentiation matrix, the above differential equation just becomes like this. So now no need of writing all those steps. It is just simple. You can write like this. So a naught into d square y plus a1 into dy plus a 2 times y. So here a naught is the coefficient of y double dash, that is 1 plus x square. A1 is the coefficient of y dash, that is 1 4x. So therefore this will be evaluated at the collocation point. So therefore this a naught a1 will impact only on the diagonals of this differentiation matrix. So hence we can write that a naught is a diagonal matrix like this, a1 is the diagonal matrix like this. So therefore this a is equal to a naught times d square plus a1 times d plus 2i is a differential matrix. So this is a differential operator and it is a differential matrix. Into y is unknown vector is equal to 0. So it is a homogeneous system, but we have a boundary conditions. That boundary conditions can be implemented uh, at the first row and last row. So the right boundary condition is implemented at the first row, and left boundary condition is implemented at last row. Uh, Last row. Then solve that resultant system of equations. Then we'll get the required solution. So how to implement this boundary conditions is very important, because we have mapped the interval -1 to 1 into 1 to -1. So 1 is the x naught and -1 is the xn. So we are just inverting that interval. Therefore, the endpoints are just switched. So implement that boundary conditions in that matrix in this form. So y of 1, the right boundary condition is off. So that is implemented at the first row. This is the first row, changes in first row of the matrix. And y of -1 is 0.5. That is implemented at the last row. It is supposed to be n plus 1 at last row. This is n plus 1. Yes, sorry for that, it's the typing error. So implement that the last row. So it is given here. So the last row. Then solve this by using any of these softwares. Program this entire procedure by using MATLAB or Mathematica or Python and so on. Then we'll get the required result in this form. You can observe that this equation is having an exact solution. The exact solution of this differential equation is 1 over 1 plus x squared. So the approximate solution and the exact solution at each collocation point or each node is same. And the number of nodes which is deposited here is at the boundaries. You can check. This is the very important point I explained. So the collocation points deposited near the end points of the interval is more. So therefore, this plays a very important role in boundary layer theory. So this is the required solution. You can see that both the approximate solution and the exact solution are they're almost same. So if we calculate the error in this solution, you can check that this is error at each collocation point is given. So the collocation, since the near the intervals, the endpoints of the interval is very important. So here the error is So it is 2 into 10 power minus 9. So the error is almost 9 digits accuracy we got. So error is very small. So therefore, this method is works very well. But so one has to remember that this method is works well only for a smooth problems or the smooth solution problems. So it has a that is a disadvantage whenever you have a discontinuities in the solution, then this method will not work well. So that is the one of the disadvantage of this method. And also the other disadvantage, the limitation of this method is this stability of the method is not well established. So that is the another the limitation of this method. So then I'll consider one the examples from fluid mechanics as a nonlinear differential equations. I'll just demonstrate how to solve this nonlinear differential equations using this collocation method. But so this is the nonlinear differential equation. So f is the nonlinear operator and subject to the following boundary conditions: G A, that is left boundary condition, GB, right boundary conditions. So here F, G are nonlinear operators. So then how to use the spectral collocation method to solve this nonlinear differential equation? So to solve this nonlinear differential equation, first we must reduce this into linear form. So how to reduce this equation into linear form? We use by method called Quasilinearization method. So how to apply this Quasilinearization? It is just a simple procedure derived from Newton's method and Taylor series expansion. So this quasi-linear method approach assumes that difference between the approximate solution at the present iteration and previous iteration is very small. Suppose YR is the solution at previous iteration and YR plus 1 is the solution at the present iteration. So this difference, absolute value or absolute difference, is very small. If this difference is very small, then that nonlinear operators we can expand as a Taylor series in multivariables about this point YR. So therefore, this method will give rise to wherever you have a nonlinear term, that nonlinear term can be written as can be decomposed into the values at the previous iterations into values at the present iterations. So we'll use the Taylor series expansion in multivariables to that expand that nonlinear operator about this assume the solution at the present iteration. So YR. So expand that. This is the Taylor series expansion. You observe that this is the since right hand side of that nonlinear operator is 0, so we'll get this entire series, infinite series, is equal to 0. So then this first value, it is a value of the nonlinear operator at YR, so it is known, and dou by dou f by dou yp. So this is the derivative of that nonlinear operator with respect to yp. This is also known at YR. So only unknown term is this YR plus 1p. So minus YR. So the P represents the iteration derivatives here. P represents the derivative. So therefore this YR plus 1P is the unknown and remaining all other terms are known. So therefore you keep the term with this YR plus 1 in left hand side and take all other terms to right hand sides. We get the equation of this form. So this, you observe that left hand side YR plus 1, so that is the unknown terms, and right hand side is completely known. So now this dou f by dou yp, which is a derivative of that nonlinear operator with respect to the y's, is known. The only unknown is YR plus 1. So therefore it is a product of known into unknown, so it is a linear. So it becomes a linear, and right hand side everything is a known. So because everything is at YR, so everything is known, so therefore this different nonlinear operator f becomes the linear differential equation. So because yp it is, p represents the derivative, so this is still a differential equation. Then once you have linear differential equation, you can use Quasilinearization approach to solve this linear differential equation. So that you can write in more compact form. Just expand this summation on left hand side and write that dou f by dou yp as a coefficient of yr plus 1 in the following form. So write it as a naught r yr plus 1 n derivative a1 r yr plus 1 n minus 1 and so on up to a n r y r plus 1. So non-derivative term is equal to rr of x. So this rr of x is the it's a linear term and it is known at the present iteration. So therefore, only left hand side contains the values of the next iteration. So hence we need to use the iteration, or we need to use looping statements to run this program while programming using some software package. So here, what is this a naught r is nothing but derivative of that nonlinear operator with respect to yn, and a1 r is the derivative of nonlinear operator with respect to yn minus 1, and so on. So a n r is also derivative of nonlinear operator with respect to y. So on the right hand side, it is just the mm, the expression, this expression of this equation, left hand side of this expression minus the nonlinear operator at yr. So if simplify this, we'll get only the nonlinear terms that will be pushed onto right hand side, and they will be known at because they are at the previous iteration. So then I'll just demonstrate this method to solve the examples from fluid mechanics. So let us consider the following nonlinear differential equation of the form, so y triple dash plus 2 times alpha times re into y dash plus 4 times alpha square y dash is equal to 0. So this equation is called Jeffrey-Hamel equation. So it is a third order differential equation. Here alpha is the angle angle, and re is the Reynolds number. So let us consider this differential equation subject to following boundary conditions. So it is y of 0 is 0 and y dash of 0 is 0, y of 1 is 0. So the interval here, interval of interest is 0 comma 1. So the interval is 0 comma 1. So but first let us convert this as a nonlinear differential equation, because we have y into y dash, the product of unknowns are multiplied here. So nonlinear differential equation. First let us reduce this into linear differential equation by using Quasilinearization scheme. So to use the Quasilinearization scheme, let us assume that the yr is the some initial guess. So some initial guess at the present iteration. So then I'll expand this the nonlinear operator about this yr as a Taylor series by using multivariable Taylor series. So that if I expand, then I'll get this following. This is from the Taylor series. After shifting all the terms with suffix r to right hand side, we'll get this expression. So as I mentioned in the previous slide. So this is a naught r into y triple dash plus a1 r into y double dash, and so on is equal to rr. So rr is the right hand side, which will be completely at rth iteration, whereas left hand side is as r plus 1th iteration. So now how to find a naught r? A naught r is nothing but differentiation of this nonlinear operator with respect to y triple dash. So if I differentiate with respect to y triple dash, then I'll get so it is dou f by dou y triple dash is just 1, and a1r is nothing but derivative of f with respect to y double dash. There is no y double dash term in this equation, therefore we get that is equal to 0, and a 2r is nothing but derivative of f with respect to y dash. So if I differentiate f with respect to y dash, so we have term here y dash term. So this coefficient 2 alpha re dou y, and here also we have y dash, so 4 alpha square. So that is your dou f by dou y dash. Then a3r is differentiating f with respect to y. So if I differentiate f with respect to y, I'll get this 2 alpha re y dash. So it's a partial derivative. So therefore we'll get y. So these are the coefficients of that expression. Then computing right hand side term. So this is the expression of differential equation at rth iteration minus this is the given differential equation at rth iteration. So simplify this. You can check that this a naught r y triple dash. So this term, this is 1, and this y r triple dash get cancels. Similarly, there is no y double dash r, so this term will go to 0. And a2r is 2 alpha re times yr plus 4 alpha time yr dash. So taking this product with this, and here we have 2 alpha d yr y dash. So this with negative sign, one term get cancels, and this is 4 alpha yr dash, and here it is minus 4 alpha yr dash get cancels. So this term cancels with these two terms after substituting this a to r. So then we'll left out with only this term. So it is a3r is 2 alpha times re into yr dash into yr. So we'll get that term remains. This is a completely nonlinear term in the differential equation. You can check that this is the nonlinear term. So now it is evaluated at rth iteration, and that is pushed to right hand side. So we'll get right hand side like this. So now, so since it is the equation is linearized, now I'll use the spectral collocation method with Gauss-Lyapunov points and Lagrange polynomials as a basis function. Then this equation becomes just the system of equations uh, with the yr plus 1 as unknowns. So then solve this system of equations, we'll get the required solution. But since we are using a Lagrange's polynomials, the derivatives here derivatives in this step. This y triple dash, I'm assuming a solution, the series solution of this by Lagrange's polynomial. So the y triple dash is nothing but L triple dash. So L triple dash means it is a d cube. And similarly here it is L double dash, so it becomes d square. And here it is L dash, that becomes d. And here it is non-derivative, just L, so that becomes identity matrix of order n plus 1 by n plus 1. So hence that differential equation becomes like this. So A is equal to d cube plus a2r times d plus a3r times I. So here this coefficients a2r and a3r, they will be having impact only on diagonal elements. So that I've written it as diagonal of a2r and diagonal of a3r. So this system a into y, where yr plus 1 is unknown. So the value of y at x0, x1, x2, so on up to xn. And r is the right hand side values. They are the values of nonlinear terms at the present previous iteration. Then impose the boundary conditions on this. There are three boundary conditions. At x0, it is 0. At xn, that is 1, it is 1. And this is at the n plus 1th row, and this is at the first row, and this is at the nth row. There are three conditions. Therefore, the third condition you impose on nth row, then the corresponding changes in the matrix. This is with respect to programming. So the corresponding changes in the matrix happens in the respective rows given here. So it is first row, n plus 1th row, and this is nth row. So nth row, it is a derivative conditions. Therefore, we'll get that derivative at the last point, because this boundary condition at the last point. So therefore, we'll get the values of derivative at that last point. So then solve this by programming. So we'll get the numerical results like this. So this is the velocity profile for different values of Reynolds number. You can observe that as the Reynolds number increases, the velocity is increasing. So this is the required result. Then also determined where to compare the exact values and this present method. So it is a spectral Quasilinearization method. So also determined what is the screen friction values. Okay, y double dash of 0. So y double dash of 0, it is near the left wall. The exact values of screen friction are given like this with respect to different Reynolds numbers. For Reynolds number 10, so you can check that almost 8 digits are same. So I just fixed that programming for 8 digits, so it is 8 digits, but it is exactly same as this exact one. Similarly, this is at 50, so it is same. Up to 8 digits, it is same. And this is at 100, up to 8 digits, it is same. So therefore, the this spectral collocation method, along with quasi-linearization, is highly accurate for boundary value problems. Also, but it will not work well for the problems having discontinuities. And that drawback I already mentioned. So let me. That is the first example with respect to fluid mechanics. So further, let me consider one more example with the system of equations. So this is the one of the problem taken from SS Morsa. So this is a coupled system of equations where U represents the temperature, V represents the velocity. So this is a nonlinear differential equation. HA is the Hartmann number and RE is the Reynolds number. So this system of equations to be solved subject to this boundary conditions. So since this is a nonlinear differential equation, we have a system of equations. So you can take this as a operator F, and this you can take it as a G. So F and G are nonlinear operators. So you take that F and G, then you assume this solution at rth iteration as for this equations as UR and VR, and so then use this condition. The absolute value of the difference between present iteration value and previous iteration values are very small. Then you can expand this F and G as the uh, as a Taylor series by using multivariable calculus in the following form. So these are the after expanding Taylor series and taking the terms with suffix r to right hand side and keeping the terms with suffix r plus 1 on left hand side. So with this two equation, nonlinear equations becomes like this. Now you can check that a to r is a to r, a1r, the coefficients are completely at rth iteration, so there will be known values. And right hand side r1 is a known value. Similarly, this C4r, C3r, C2r, all these coefficients in second equation also at the rth iteration, so they will be known. So using this differential equation, this system of equations becomes a linear differential equation. Here the coefficients are given by here the coefficients are given by this derivatives, partial derivatives. So once you determine those partial derivatives and right hand sides, will get like this. So this is the right hand side of first differential equation after taking the terms with the suffix r to right hand side, and these are the nonlinear terms in the second equation. You can check that this is completely nonlinear term in first equation, and there's a nonlinear term in the second equation. So after using quasi-linearization, this entire nonlinear term will be known at rth iteration, so it is pushed into right hand side. Similarly, this is also at rth iteration, and that will be pushed into right hand side. So these are the right hand sides of that linear equation now. So then what we do is we use a spectral collocation method to uh, get the solution of this. So I'm using here the Lagrange's polynomials as a basis functions along with Gauss-Lioberto points as the collocation points. So once we use Lagrange's polynomials, this derivatives u double dash means it is L double dash means it is d square as I explained. Similarly, u dash means it is just L dash is d, u means L, so it is just I, and similarly v dash means it is just L dash, that is d, and v means it is I. So that the derivatives becomes just a spectral differentiation matrices. So then after applying that spectral differentiation matrix, this system of equations become like this. Now we check here, D is the differentiation matrix. It is n plus 1 by n plus 1 matrix. So I is also n plus 1 by n plus 1 identity matrix. So this system we can put in this following matrix form. So this you can take it as A11, A2R D square plus A1R D plus A0 R I is A11. Similarly, B1R D plus BR0 as I. And similarly, second equation A21 is 0 and A22 is this operator. Then u into ur plus 1 is a vector, because this ur plus 1 is the values of u at different collocation points. Vr plus 1 is also a vector, so because it is a values of v at different collocation points starting from x0 to xn. And these are the non-linear operators, but they are at the rth iteration, so they are known. So this is a system of equations. You solve this system of equations by any method, then we'll get the required solution. So these are the results presented here. You can check for different Hartmann numbers. It is just compared what are the values of shooting method and the spectral method. So you can check that the actual values are these are the not actual values. They are just calculated values. So but actual values are very close to this. So almost the 7 decimal places are same as this spectral method. This is for 0, and this is the u dash of 0. and the screen protection here and another result number here. So this is for Atma number 5, and up to 7 to 8 decimal places values are accurate, and this is for 10. And this is the temperature profile for different values of Atman number, and this is the velocity profile for different values of Atman number. So therefore, this again, I'm saying that this collocation method or pseudo spectral method is which matches very good for solving the boundary value problems. So again, I hope there is some time, so I'll just quickly take one more examples, but I'm not giving in detail. I'll just show that how this method is accurate. So this is the another system of equations from fluid mechanics, boundary layer flows with respect to this boundary conditions. I just show this how to quasi-linearize, because this is a nonlinear operator. So this is nonlinear term here, and this is only nonlinear term, and this is a nonlinear term here. So you take this as f g h, then assume this solution at rth iteration, then expand this as a Taylor series in multivariables, then take the terms with suffix r to right hand side and keep terms with r plus 1 suffixes r plus 1 on left hand side. Then we can find out those coefficients using this, and this is the nonlinear term in first equation, nonlinear term in second equation, and this is a nonlinear term in third equation. Then assume this solution by using Lagrange's polynomials for first equation, first variable, second variable, and third variable. Then use the Gauss-Lebedeau points as a collocation points. Then solve for here. Instead of solving, I just determine the residuals. These are the residuals in that three field variables. So this residuals is calculated, and you can observe that the residuals having almost 10 power minus 10. So it is up to 9 decimal places of accuracy. So there has a number of collocation points are increased. So this is for 30, n is equal to 30. The accuracy is the 10 power around 10 power minus 7, and n is equal to 70. It is accuracy is after 10 power minus 10. So this is the residual in the first field variable, and this is the residual in second field variable theta. So it is again n is equal to 30. It is around 10 power minus 9, but n is equal to 70. Number of collocation points I'm saying, n is equal to 70. It is around 10 power minus 11. This is the residual in second field variable, and this is the residual in the third field variable. And these are the few references. I suggest that those who are want to start this method, they can refer this Ellen Trefton book titled Spectral Methods in MATLAB. This is a very good book. Also, the Husseini and John Boyd books also very good. So that's it. Thank you very much. So if you have any questions, I'll take over questions. Hello.
Yes, sir.
Madam, I'm done with madam. So
yes, sir. Thank
very
you for
long.
the effective session, sir. There is a question from a participant.
Yes, madam.
How to solve an equation set with mixed boundary conditions?
Mixed boundary conditions. It is actually implementation of a boundary conditions is again it is a different topic. You can implement, but I think if they contact separately, I'll answer that question, madam. So it is again I need to answer that I need to show the programming part. So if you have regarding that question, if that person contacts me directly, I'll explain that. I'll just give the suggestions and inputs on that.
Okay, sir.
Any other questions, ma'am? Limitation of the method.
There's one more question from a participant named Divya.
Okay, yes, ma'am.
For converting nonlinear coupled PDE to ODE, which method can I use other than similarity transformation? Is there any alternate method?
Yes, madam. So you can use Fourier transform technique. So there are alternate methods. You can use Fourier transform technique for that. This, there is one more question. It is a coupled differential equation stability. Uh, yes, you can solve. The stability of this method is not generalized. There's no general theory for this. Is derived for this method. So only the particular type of problems, the methods are the stability of particular problems is derived, but general stability analysis is not available for this method. Yes. Any other question, madam?
Sir, how to find solution of Schrodinger's second order differential equation?
This Schrodinger second order. Actually, there are few papers that use this method to solve Schrodinger equation, but again, it is because it is in a complex plane. And also it is a nonlinear differential equation. One has to use the quasi-linearization to first reduce it into linear differential equation. Then definitely one can use this collocation method. But you have to think about the basis functions. So I think the basis functions in terms of first Fourier transforms or Fourier coefficient or orthogonal functions are I hope that answered those that question.
I think the questions are over, sir. There are no queries.
Okay, madam.
So now I request Dr. Sendil Kumar, sir, convener of FTP, to
Okay.
propose the vote of thanks.
Thank you very much, madam.
Good morning, everyone. I deem it my privilege to propose my vote of thanks. First of all, I thank our honorable resource person of today, Dr. G. Chandrasekhara, for sharing valuable insight on spectral quasi-linearization approaches for solving boundary value problems in fluid mechanics. I also extend my sincere thanks to Dr. Abdul Hakim for his wonderful presentation on yesterday's session. I thank our management for their support. I thank our respected principal, Dr. V. Vijaya Samundishwari, for her guidance to organize this webinar. I also express my thanks to our Vice Principal, Dr. Suresh Kumar, for his support. I extend my sincere thanks to Dr. P. Vignesh Kumar, Head of the Department, for his encouragement. I extend my thanks to all the active participants who patiently cooperated the webinar and took it in a successful manner. I congratulate Ms. Shruti, coordinator of this webinar, for their contribution and involvement. My thanks to the ICT team also for their support. My heartfelt thanks to our friends and family for their hold up in this pandemic period. Once again, thank you all.
Thank you, sir.
Thank you, sir. Thank you so much.
Thank you.